Hello, this is a video supplement to the article First Principles Molecular Dynamics Modeling of the Molten Fluoride Salt with Chromium Solute, published in Journal of Nuclear Materials. This video is presented by Hyun Nam from the University of Wisconsin-Madison. This study employed the First Principles Molecular Dynamics method to study the thermokinetic properties of molten fluoride salts. The calculated thermokinetic properties of pure salts, such as density and self-diffusivities of salt constituents, were in good agreement with the experiments. The strong bonding between the chromium and fluorine at higher charge states were observed from the modeling of a dissolved chromium solute in molten salts, and this explains the slower diffusion of chromium 3+. We are interested in molten fluoride salts because they are being considered as a coolant for the next generation nuclear reactor systems. In this study, two representative fluoride salts for nuclear reactor systems, FLive, a contraction of its constituents fluoride, lithium, and barium, and FLiNac, with its constituents fluoride, lithium, sodium, and potassium, were investigated by using first principles molecular dynamics, which is a well-suited simulation method for Ricky system. Thermodynamic properties, diffusion coefficients, and local structures for both pure molten fluoride salts and fluoride salt with dissolved chromium solute were studied. Selection of the exchange correlation functional is important in first principles calculations. We test several exchange correlation functionals against two experimental equilibrium volumes of molten FLive. Normal PV potentials overestimate the equilibrium volume. By including van der Waals dispersion forces, we predict the equilibrium volume to within the experimental range, and thus we use the van der Waals DF method with the PV potential for this study. With the selected exchange correlation functional, thermodynamic properties of fluoride salts, such as the density, Vörtler modulus, and coefficient of thermal expansion, were predicted and are consistent with the experimental measurements. We calculated self-diffusion coefficients of the molten salt constituents from the first principles molecular dynamics and compared them to the experimental measurements. The calculated diffusivity of lithium in FLive is about 3 times lower than measurements, but we matched the activation energies almost exactly. Diffusivities of fluorine and barium were also predicted. For the fluorine diffusion, extraordinarily high activation energy of experimental fluorine diffusion was reported. However, given the result for lithium in FLive, there is no reason to expect a significant error from the calculated fluorine diffusion. Diffusivities of lithium, sodium, potassium, and fluorine in FLiNac were also calculated. All these ions possess similar diffusivities and consistent trend was observed. As in the barium diffusion in FLive, FPMD can be used to generate the data where no measurements were made. The behavior and diffusion properties of chromium solutes in fluoride salts were also studied. Local atomic environment of chromium solutes on the different oxidation states are shown here. Chromium 3+ makes a stable octahedral structure with 6 bonded fluorine. On the other hand, chromium 2+ ion forms various coordination polyhedra with fluorine, and the neutral chromium shows very weak bonding to fluorine. We can clearly see a significant local structure difference. We quantify this trend with the radial distribution function between chromium and fluorine. The integrated radial distribution function for chromium 3+ shows 6 neighbor fluorine ions, consistent with the octahedral structure as can be seen in the movie. In the same manner, the radial distribution functions and coordination numbers for chromium 2+ and neutral chromium shows a very loose structure for neutral chromium with the chromium 2+ in between. The local structure difference carries over for the diffusion properties of these different chromium ions. We see that the neutral chromium is the fastest, next is the chromium 2+ and chromium 3+. The lower diffusivity of chromium 3+ can be explained by the stronger bonding between the chromium 3+ and fluorine. The octahedral cage prevents chromium from easily moving through the molten liquid. The successively reduced local structure for chromium 2+ and neutral chromium allows them to diffuse faster. In this study, first principles molecular dynamics was employed to calculate the thermokinetic properties of molten fluoride and free negative salts. Density, bulk modulus, coefficient of thermal expansion, and self-diffusivities of salt constituents are in good agreement with the experiments. Local structure analysis for the dissolved chromium solutes on the different oxidation stages exhibits strong chromium 3+ bond with surrounding fluorine ions. This explains the lower diffusivity of chromium 3+ compared to chromium 2+ and neutral chromium. For more information about this study, please find our article in the Journal of Nuclear Materials. Thank you for watching this video supplement.